Data science is like baking a cake. It sounds simple at first. You follow a recipe, mix ingredients, and pop it in the oven. But what if the recipe is vague? What if your ingredients are past their expiration date? Data science faces similar challenges. We start with messy data and ambiguous questions. Our goal is to turn this mess into delicious insights. But it's easy to get lost along the way. We need the right tools and principles to guide us. Think about using a navigation app. You want to get from point A to point B. The app uses data from satellites and maps to calculate the best route. You trust the app because it has a history of accuracy. It's predictable. You also trust that it won't take hours to calculate your route. It's computationally feasible. And you trust that the app will adjust if you miss a turn or hit traffic. It's stable. Just like a reliable navigation app, responsible data science requires a framework for trustworthiness. That's where PCS comes in. Data science, at its core, is about extracting knowledge from data. This knowledge helps us understand the world better. It also helps us make informed decisions. But the quality of those decisions depends on the quality of our data and analysis. If we're not careful, we can end up with misleading results. This can have real-world consequences, impacting people's lives in significant ways. Imagine a medical diagnosis based on a faulty algorithm, or a self-driving car that misinterprets data from its sensors. These examples highlight the importance of doing data science right. We need a system that ensures our findings are reliable, responsible, and trustworthy. This is not just about getting the math right. It's about understanding the limitations of our data, and it's about being transparent about our assumptions. This is where the PCS framework comes into play. The PCS framework acts as a guiding principle for data scientists. It ensures that our work is accurate, reliable, and applicable in the real world. Let's break down each component. Predictability. A good model should make accurate predictions about future data. If we're analyzing customer data, for example, our model should accurately predict future buying behavior. This reliability builds trust in the insights derived from the data. Computability. The methods we use should be computationally feasible. In other words, we should be able to run the analysis within a reasonable time frame using available resources. Stability. Our results should be stable and consistent. Minor variations in the data should not lead to drastically different outcomes. A stable model is robust and trustworthy, providing consistent results even with slight data fluctuations. These three pillars work together to ensure that our data analysis is sound. They provide a framework for evaluating the reliability and trustworthiness of our findings. By adhering to the PCS framework, we ensure that our work is not just accurate, but also applicable and impactful in real-world scenarios. Imagine you're checking the weather forecast. You see a prediction for sunshine and clear skies. But when you step outside, it's pouring rain. You might start questioning the reliability of that weather app. The same applies to data science models. Predictability is all about the accuracy of the model's predictions. A good model should be able to generalize beyond the data it was trained on. It should be able to make accurate predictions about future unseen data. This is crucial because in most cases, we're interested in using data science to make decisions about the future. For example, let's say we're building a model to predict customer churn for a streaming service. We train our model on historical data of customers who canceled their subscriptions. The model identifies patterns and factors that contributed to those cancellations. A predictable model would then accurately identify customers who are at risk of churning in the future based on similar patterns. To achieve predictability, we need to carefully select our data, choose appropriate algorithms, and rigorously test our models. We need to ensure that our models are not overfitting to the training data. Overfitting is like memorizing the answers instead of understanding the material. An overfit model might perform well on the training data but fail to generalize to new data. Section 4, Computability, is it feasible? So standing strong against the tide. And now responsible data science, a partnership between human and machine. Subscribe for more videos. Thank you.